All right, let's jump right in. Today, we are undertaking a really fascinating journey into the very essence of artificial intelligence in this explainer. To truly grasp what AI is today, and honestly, where it's going tomorrow, we need to look at it through a unique lens, the metaphor of the mind and the body. By combining some cutting-edge microchip benchmark data with groundbreaking legal doctrine, we'll see exactly how these two vastly different worlds collide. We're going to seamlessly bridge deep philosophical theories about the machine mind with the raw silicon hardware realities of the machine body. And as you'll see, doing this reveals the massive legal paradoxes that emerge the second we deploy these systems into the real world. Here's a quick look at our roadmap for today so you know exactly where we're headed. We'll start with the roots of AI, move into classifying the machine mind, check out edge computing and SLMs, then look at the hardware powering AI, explore consciousness and ethics, and finally wrap up with AI and criminal law. Let's get to it. Section 1. The roots of AI, tracing the origins of the machine mind. Okay, let's dive into this history. To really understand where AI is heading, we first have to understand where it came from, right? The conceptual idea of artificial beings actually goes all the way back to ancient Greek mythology, but the scientific realities started in the mid-20th century. We saw early milestones like the 1956 Dartmouth Conference that basically birthed the academic field, and pioneers introducing theoretical tests for machine intelligence like Alan Turing. But for decades, the field was trapped in these cyclical AI winters. You see, the underlying mathematics existed, but the hardware simply didn't. Funding repeatedly dried up. That is, until the 2020s. We are now living in a true deep learning renaissance. And what pulled us out of the winter wasn't just new algorithms. It was the explosive evolution of compute power. Specifically, we're talking about parallel processing on massive GPU clusters, which finally gave those complex neural networks the raw horsepower they needed to process mountains of data. Moving on to Section 2, classifying the machine mind. Understanding intelligence levels. Think about it. Literally everything we interact with right now falls strictly under narrow AI. Your phone's voice assistant, medical image scanners, autonomous driving algorithms, they're all highly specialized. They can perform one specific task incredibly well, often detecting patterns way faster than any human expert could. But here's the critical limitation we have to remember. Narrow AI has absolutely no general understanding or common sense outside its specialized domain. If a self-driving car encounters a bizarre, never-before-seen physical obstacle on the road, it doesn't pause to reason about the context of the situation, it just blindly executes its programmed weights. This exact lack of general reasoning and contextual awareness is what creates the massive, fatal liability loopholes we're going to dissect later in this explainer. On the exact opposite side of the spectrum, we have strong AI, which is a theoretical machine mind possessing broad, human-like cognitive flexibility. And this brilliantly illustrates what happens if we eventually cross that threshold into strong AI. We hit artificial general intelligence, or AGI. At this point, the machine can perform literally any intellectual task a human can. But the scale doesn't stop there. Once a system can learn, code, and reason exactly like a human, it can theoretically improve its own architecture at digital speeds, leading to artificial superintelligence, or ASI. This fundamentally changes the whole paradigm. At the ASI level, an entity surpasses the brightest human minds in every conceivable discipline. And, more importantly for our discussion today, an ASI would iterate its own cognitive processes so rapidly that it fundamentally breaks the chain of human legal oversight. Seriously, how could any court possibly regulate or assess the intent of an entity whose decision-making process is fundamentally beyond human comprehension? Section 3. Edge Computing and SLMs, the physical body of modern AI. So let's bring it back to present-day reality and zoom in on that physical body. You've likely heard a lot about massive, large language models running in the cloud, but running those requires staggering computational infrastructure. Enter small language models, or SLMs. These are highly optimized, lightweight alternatives, often sitting well under 7 billion parameters. They are intentionally designed to bypass server farms and fit right within the tight memory and power constraints of local devices. They bring advanced inference out of the cloud and directly onto the physical endpoints in our pockets and homes. We call this operating at the edge. So why does deploying SLMs at the edge matter so much to us? Well, imagine a portable medical diagnostic tool operating in a remote area without internet access. It needs to detect a critical anomaly in real time. It simply can't afford the latency of waiting for a cloud server to respond. SLMs solve this by processing the data entirely offline, meaning decisions are made instantly and bandwidth usage is slashed. But fundamentally, this drastically improves user privacy. In our medical device example, highly sensitive patient health data never leaves the room. This localized approach is completely revolutionizing how we securely integrate AI into high-stakes, real-world environments. Section 4. The hardware powering AI, CPU versus GPU versus NPU. Now, what's really interesting about this slide is the division of labor we see on the hardware battlefield. Based on recent 2025 benchmarking research published on Archive, we can pit the biggest microchip architectures against each other. At the top, we have standard CPUs, which remain fantastic for general, everyday computing and low-power standby tasks. Then we have GPUs, the traditional heavy lifters for training massive AI models, mostly because of their extreme parallel processing power. But the true game changer for edge deployment is that bottom row, NPUs, or neural processing units. The benchmark specifically highlights custom hardware like the Raider chip NPU. You guys, these aren't generalists. They are silicon architectures built from the atomic level up, specifically to execute the massive matrix multiplications required for AI computation. This positions them to entirely dominate specialized SLM inference right on your device. Visually, the benchmark findings completely confirm this architectural dominance. When running these small language models locally, NPUs achieve the highest performance by a massive margin. But in edge computing, raw speed isn't actually the most important metric. Battery life is. That's where the energy delay product, or EDP, comes into play. EDP is the ultimate metric for edge devices because it measures the exact balance between execution time and energy consumed. And the research data is staggering. While low-power ARM CPUs put up a good fight for basic idle energy usage, when you combine rapid inference speed with power efficiency, the NPU just obliterates the competition. The benchmarks show custom NPUs achieving an energy delay product up to 30 times better than traditional architectures running the exact same localized model. They are, for sure, the undisputed engine for the future of mobile AI. Section 5. Consciousness and Ethics. Returning to the mind. Okay, let's zoom back out from the tiny power-constrained microchips for a second. To really understand the ethical weight of these advancements, we need to define autonomy, a system's ability to make decisions without direct human supervision. Those incredibly efficient NPUs and SLMs we just discussed are exactly what physically grant this autonomy in the field. By entirely severing the tether to the cloud, the machine is now capable of making high-stakes decisions completely independently in the physical world. But here is the million-dollar question. Does an autonomous machine actually know what it's doing? The philosopher John Searle's famous Chinese room argument asserts that even perfectly simulated intelligent behavior is not equivalent to true understanding or consciousness. Consider an autonomous vehicle forced to make a split-second life-or-death swerve. The NPU crunches the matrix math flawlessly to execute the maneuver. But it doesn't know it just ended a life to save another. It feels nothing. It possesses absolutely no morals. It's literally just executing optimized weights and biases. And that creates a massive, totally unprecedented headache for our justice system. Section 6, AI and Criminal Law, Society's Ultimate Rulebook. To explore this, we're drawing on a really comprehensive 2024 doctoral dissertation from the University of Luch, Faculty of Law and Administration. This groundbreaking research painstakingly highlights a massive legal gap regarding the core criminal concept of mens rea, or the guilty mind. For centuries, criminal law has required an actor to have malicious intent or extreme recklessness to be held truly culpable. But how on earth do you prove mens rea in a piece of silicon that totally lacks consciousness? The dissertation reveals that our entire penal code, which fundamentally assumes human agency and moral awareness, is drastically unprepared for entities that act autonomously in the physical world but possess no actual mental state. So the crucial point is how the law must untangle this incredibly complex web of hardware and software when a tragedy actually occurs. According to the research, courts are forced to navigate a highly problematic multi-step process. First, they must identify the creator's responsibility. Did the developers fail to build in proper safety constraints? Well, the problem here is the black box nature of deep learning. Even the creators often cannot explain exactly how a neural network weighed its parameters to reach a specific output. That makes gross negligence extremely difficult to prove in court. Second, they must assess the user's intent. Was the edge device deployed maliciously? If a human merely turned on an autonomous tool they reasonably believed was safe, assigning them a guilty mind is legally fraught. Finally, the court must evaluate the machine's level of autonomy. If the NPU processed an SLM to make an entirely independent, localized decision that resulted in a fatality, the traditional lines of legal blame completely shatter, leaving victims with no clear entity to hold legally accountable. which leaves us hurtling toward an existential collision with our own legal system. As our edge hardware becomes vastly more efficient and our software models operate with increasing physical autonomy in the real world, we face an unprecedented societal crisis. If an autonomous system commits a crime, who goes to jail? It's a question we are